Hi, I am the presenter for this project. My name is Junyi. The author for this project are Junyi, Chiew, Shirley, and Elfadil. The project name is Efficient CNN-based Maize Leaf Disease Detection for Abandoned Agriculture Applications. The content got 8. The firstly will cover for abstract. This project aims to develop an efficient corn and maize leaf classification system using transfer learning on CNN. Deep learning is used in this project due to the training algorithms are involved. Training and evaluate process is conducted on the Google Colab, and it will explore the train model on the Jackson Nano. Problem statement. Corn has a high economic value and a wide range of benefits because it can be processed into food, industrial raw materials, and a source of animal feed. Second, diseases in maize dismiss the productivity, which is a major cause of economic damage in the agriculture business throughout the world. Thirdly, maize leaf disease mostly result in the lower yield and economic losses for farmers. Objectives. This project got 3 objectives. First, to design a computer vision model using transfer learning for classify the plantation disease. Second one, to quantize the train model to achieve lightweight for abandoned device application. Third, to analyze the performance of accuracy in quantized and unquantized models. So this is the scope of work. The dataset got 4 classes which consist of 4,187 images. The model design and transfer learning using Google Colab. Quantization on the models to reduce its size and optimize it on the abandoned device. Then it will integrate the models into the Jackson Nano at a local environment for real-time testing. So this is the Google Colab. And this is the dataset classes which got 4. Blight, common rust, grey leaf spot, and a healthy. So next is methodology. Inside the methodology, we're starting from the data preparation. So we'll get the corn or maize leaf dataset from the Kaggle, then split the dataset into the trend and val folder. Next is for training the models. This phase involves the scheduling, the learning rate, and saving the best models. It will save the best models named as the best model param.pt inside the folder that I set on my Google Drive. Next one is fine-tuning on a ConvNet. It load a pre-trained models and reset the final fully connected layers. Fine-tuning a pre-trained ResNet 18 models for a classification task with 4 output classes. The optimizer used is stochastic gradient disease (SGD), which adjusts the model's parameters during the training to minimize the losses. So next is train and evaluate. It will undergo 25 times of the epoch that the models will be trained. The output will have train loss and validation loss for each epoch and show the best validation accuracy and the training time taken when it is complete the training. Then it will continue with the ConvNet as a fixed feature extractor. It frees all the network except the final layers, which mean their weights will not be updated during the training, and the original final connected layer is repasted with the new dataset with 4 output classes. Then it will interface with custom images. It use a train models to make the prediction on the custom images and visualize the predicted classes labels along with the images. So in this inference custom images, I chose the predicted classes is for the healthy classes. So next is training a custom classifier based on a quantized features extractor. It load a pre-trained quantized version of a ResNet as a models, then modify the models by replacing the last fully connected layer with custom classifier for the dataset. Then set the loss function and the optimizer. After that, continue with train and evaluate the models. So this is the result for one of the epochs that I get in the training. So the next one is fine-tuning the quantizable models. It uses a quantized pre-trained features extractor and fuse layer. Then create the combined models and insert the fact quantization models. Fine-tune the models and convert to the fully quantized models. After that, test and evaluate, then save the best model as a quantized model for the embedded device. This one is for the accuracy check. So it need to evaluate the quantized model's accuracy and check if the accuracy is not good, then we'll need to undergo again for the fine-tuning for the trainings. Next one is analyze the performance of accuracy in the quantized and unquantized models. So this project will do a comparison between the quantized and unquantized models for their accuracy. For the left hand side is the unquantized models and the right hand side is the quantized models. After done analysis the performance accuracy, we will continue with the real-time testing on the Jetson Nano. In this methodology, we'll integrate the models into the Jetson Nano local environment for real-time testing. So firstly, we'll need to install the Jetpack for the Jetson Nano developer kits. The version selected is 4.6.1. Then we'll need to write the image to the micro SD card. Then format the SD card and flash the Jetpack to the Jetson Nano developer kit to the SD card. So this is the result photo for the done flashing to the SD card, and this is the setup for the Jetson Nano and the webcam. After that, we'll run the code on the Jetson Nano to see the webcam is work functionally on the Jetson Nano, and to stop the simulation, just need to tap Q to stop it, and the camera will shut down. So this is the part of results. So the results will split into 90-10 ratio, 80-20 ratio, 7-30 ratio, and 60-40 split data ratio. So this is the result for 90-10 split data ratio. So this is for the unquantized models. Quantized models. This one is for 80-20 split data ratio. This is the result for 70-30 split data ratio. This is the result for 60-40 split data ratio. Inside the training, the best accuracy for the unquantized models is 90.15%, which is at the split data ratio. So this we can see that the epoch at 21 will get the highest validation accuracy, and for the quantized models, the best accuracy is 97.01% at the epoch of 21 also. So this is the comparison for the both side far. We can see that the quantized models file size is more smaller compared to the unquantized models. This too far is the best model param.pt. So this is the result for using the webcam and get the result using Google Colab. So the results show correctly for the each classes. So this is the Jetson Nano at the local environment to get the result to classify the mass leaf classes. And this one is using the Google Colab and the Jetson Nano to compare the output. For the left hand side is the Google Colab, and the right hand side is for the Jetson Nano. So for this one is I choose the common rust. So on the left hand side also get a common rust at the Google Colab, and the right hand side also get the common rust at the Jetson Nano, and show the outputs for their classes. Next one is Sustainable Development Goals SDG. For this project got 3 SDG, which are SDG 2, Zero Hunger, SDG 9, Industry, Innovation and Infrastructure, and SDG 12, Responsible Consumption and Production. In SDG 2, this project contributes to SDG Target 2.3, which focus on increasing the agricultural productivity and sustainable food production system. On SDG 9, this project promotes the use of the innovation technologies like AI and embedded system. However, for the SDG 12, is minimize the wastage and promotes the efficient resources utilization and aligning with the sustainable agriculture practice. As a conclusion for this project, all objectives were successfully achieved. On the objective 1, computer vision models were designed using a transfer learning to classify the plantation disease. The second one is the trend model was successfully quantized to achieve a lightweight for the embedded device application, which using the Jetson Nano. And third objective is the performance of accuracy in quantized and unquantized model was analyzed. So the project were successfully done and all the objectives were successfully achieved. That's all from me. Thank you.